Hey, hey. All right. So today, what we will be speaking about are block diagrams and feedback. So you've made it this far. This is the last, lecture of the year. Woo! Right. And by the way, we will have a review session. I know everybody's been asking about that, and I keep saying we will, and we will. All right, and it's going to be next week because I'm out of town. Well, I'm actually currently in town, but when you see this, I will be out of town. Okay, bye. All right. So, one of the things that gets used a lot in the analysis of systems are block diagrams. And there's nothing particularly fancy about them. All it is just a graphical way of representing systems. So we've kind of seen things like this in the past, where we have something like G of S. And I'm going to work in continuous time and then discrete time kind of interchangeably, because in the end, once you go to Laplace transform or Z transform, everything works out pretty similar in terms of how block diagrams work. So let's just look at the first simple thing. And we've definitely seen stuff like this in our homeworks, where they talk about, this is a cascade. That's not how one spells cascade. One spells cascade with no L's whatsoever. This is called a cascade, or series. And so the input, so what you're going to be doing here is you're going to take an input, x of t, and we can kind of equivalently represent this as its Laplace transform, right? Via its Laplace transform. And then we send it through this thing. We send it through this g, and we feed the output of the g. So the g is the transfer function, so these are just transfer functions. So we send the output of this g into the input of this h. And then the final thing we get here is y of t, which, again, we can keep in correspondence with this Laplace transform, y of s. And so this simplest system, all we have here is it just corresponds to a multiplication. Because what we're going to have here is, let's just, sometimes whenever we're doing, so oftentimes when we're analyzing block diagrams, it's useful, very useful to go give things names. So let's just give the little thing in here a name. What do we want to call it? Let's just put a letter on it. Let's call it R. All right, I'll call it R. RS is the signal in between here. So what we can do is we can give the intermediate signals names, and then just from the basic things that we've always learned here, it's that RS is equal to GS times XS, and then YS is equal to HS times RS, which is, of course, equal to HS, GS, XS. So cool. So that's how we can analyze a simple series. Or not really analyze, but effectively say what is the overall transfer function taking us from this input all the way to this output. All right, that's the simplest one. And then we have this kind of interconnection. So this thing where we feed a signal into a system, that's just kind of, taking an input and then getting an output. There's a few other operations that commonly occur in these block diagrams, and we'll just show them now with a few more examples. So I'm going to stop for a second, make sure everybody has that copied down. Okay. I don't have the luxurious board that I usually have, and so it's a little bit, harder to work with. All right, so the other operations that commonly occur are adding two signals, XF, YF. We would have two signals coming in here, and they could maybe add. And what do you want to call that signal coming out of there? Oh no! Something happened. Video saved, but seems to be too short. The file system was oh no! So sorry about this. So I was trying to compress the video from what will be Monday's lecture, and it got all whack. So sorry. Okay, we're gonna get back to this. What name do we want to give this? I say we call it T. T's not a very good name. I say we call it R again. Okay, R is a decent name. So T, I mean, people sometimes use it, but we use T for time all the time. So let's try. We've got enough letters to go around. Let's call this R of S. And unsurprisingly, R of S is equal to X of S plus Y of S. It's the addition. So I'll just keep what we had up here earlier. X of S, H of S, G of S. This is a little different. It's out of order, but it doesn't really matter. We'd have, in this scenario, Y of S is equal to H of S, G of S, X of... let me write this bigger. Sorry. Not good at predicting how much space things will take up. Y of S is equal to H of S, G of S, X of S. All right, so we've got that. All right, that's how the top system works. That's how this system works. And the last thing, very similarly, we have the subtraction. And so actually, like, one of the things that we'll do, we're not actually going to subtract things. We're not actually going to have a separate little symbol, because otherwise it's a little bit ambiguous as what's subtracted from what. So when we subtract things, oftentimes it's just denoted by this. You put a little minus sign leading into that little plus symbol, and then we know that our R of S, the result of this operation is going to be R of S is equal to XS minus Y of S. So that shows up a lot, this little negative symbol by there, just to say, oh, we're flipping the sign right beforehand. Sometimes people will actually put a little explicit box that we're mapping it through a -1. So this is equivalent, completely equivalent to doing the following thing. Well, actually, you figure this out. It shouldn't take you that long. So, what should I put? If I'm going to put a little thing intermediate into here, what should I put in that little box? All right, so stop. Spend a second for, figuring this out, not too long. Stop the video. Okay, bye. All right, start it up again. Okay, cool. So I think most of you got it. What we would put here to make a completely equivalent thing is just a -1 symbol up there. Yeah, you just put a little -1. And then the output of that thing is going to be the same exact thing. So that's how we do addition and subtraction in our block diagram notation. Some people use this, some people use that. It's a matter of choice. This is the more common thing to see, at least in control systems. And then there's one more operation that we will oftentimes see, which is multiplication. And again, the whole thing is pretty unsurprising. And you saw these things in your homeworks. Like the book would just kind of use it because it's pretty self-explanatory what's going on here. All right. Get that kind of thing. So RS is equal to x of s times y of s. All right, cool. All right, we're going to take a little pause here. Okay, we're back. So the next thing that we're going to do is we're going to go and look at a few examples of block diagrams, and then we're going to figure out what the associated transfer function corresponding to the block diagram is. All right, so let's just take something that looks like this. Oh no, I'm using the bad marker. Let's use a better marker and throw this one out. Thrown out. All right, we're going to have our x of s feeding into here, and one of the things that we can do is we can split this signal off. It's just like having two different wires or something like that. H G of s. All right, take a moment and so to go and figure out what is the transfer function that maps y of s equals to something times x of s. I'll give this thing a name. I'll call this f of s, which is fine. All right, so figure out what f of s is. Stop the video and take a moment to find that out. Okay, I saw most of you got this correct. So the way it works here, sometimes if we want to be systematic about it, we could give some intermediate signals over here. We could call this thing, we could call this thing E of s, and we could call this thing over here D of s if we so desired. And then we could go and say that we would have E of s is equal to h of s, x of s. D of s is equal to g of s, x of s. And then the final thing that we have over here is that y of s is equal to es plus ds. And if we put that together with just a little bit of algebra, we can see that this is actually h of s plus g of s all times x of s. So this must be that transfer function that we were looking for. F of s is equal to h of s plus g of s. And I can't emphasize it enough that working in continuous time or discrete time with these block diagrams, it's all the same thing. What would I do if I wanted to do this all in discrete time? Change the s to a z. That's right. We would change the s to a z, and then all of a sudden we've got the discrete time analysis. Now, for systems that are this simple, you don't necessarily have to go through all the steps of, naming all the internal signals, naming these intermediate signals. But sometimes when these block diagrams get big, it can be really helpful to name the internal signals. All right, so let's do one more block diagram one more simple block diagram that's going to introduce a very important concept here. This is sort of the most classical feedback loop. Classical feedback loop. And it looks something like this. We take our S, we have a little summing junction here, and I'm going to call this L of S. We got a Y of S over here, and this doesn't look like anything special until we do this. All right. So, take a moment and try to figure out what is the transfer function from X of S to Y of S. And actually, I will call this T, big T. And this is just for consistency with the notation that comes from control systems. All right, so pause the video and give people a few minutes to try to figure out what this is going to be. Okay, turn the video back on. All right, so what we have to do in this one, this is one of those scenarios where adding those extra variables is actually really, really helpful. Okay? So adding a little extra variable here, which also for historical reasons I will call E, because this E is denoting the error between the x of s, y of s. Having a separate name for this actually makes it a lot easier to figure out what the answer is in this scenario. Because we can just go and chuck through our rules here. We know that E of s is equal to x of s minus y of s. And we also know that y of s is equal to this. Y of s is equal to ls E of s. All right, now if the students were having trouble, if this was a challenging thing, I think this would be a good point to pause the video again and then try to complete the problem. But if everybody figured it out like it was so easy, then don't pause it. Okay, so whether or not you paused it, we're going to go on now and just figure out what the answer is. So all we need to do, once we've gotten to this point, is do a little bit of algebra. Everybody likes algebra, right? Some people don't, and that's their loss. But here's how it works, okay? We're just going to go and look at this equation and just eliminate the E variable here. And so all we've got to do is we're going to say, oh, this E is equal to, this E here is equal to that sort of thing. So I'm going to plug this in over here. Y of s is equal to L of s. Take this, chuck it in where I see the E. X of s minus y of s. And so just looking at this thing on that side, I can take the y's and bring them over. So I'm going to get 1 plus L of s. Y of s is equal to x of s. All right? And so finally, I can go and just divide both sides by this thing, and we've got y of s is equal to 1 over 1 plus L of s times x of s. So the t, so let me just kind of write it. Oh man, such a little board. All right, this thing over here, t of s is equal to 1 over 1 plus L of s. Cool. So that is the most basic feedback loop. All right, cool. So let's go and see about trying to do other kinds of things where things get more complicated. All right, so let's do other sorts of feedback loops and feed forward loops and all that kind of thing. So let's do just one more thing where we have a feedback loop, and this is something that shows up oftentimes in control systems. For example, we have x of s. We're going to have a little feedback loop that's coming through here, but then we're going to have another bit of feedback. We're going to have two pieces of feedback over here. So we're going to have our L of s that is, let's split this up actually. We're not going to have just a simple thing. We're going to have something that's C of s over here. And we're going to have another loop over here. We're going to have a minus bit coming here, P of s. And then what we're going to have is this going into, I'm going to call this big delta of s. This is y of s coming out here, and then this whole thing has a negative feedback. All right, so this is going to be a really fun challenge here. Let's go and try to find the transfer function from, x of s to y of s. So goal, find, and I'll again call it t. This wouldn't normally be called t. I'll call it g. Find g of s such that y of s is equal to g of s, x of s. All right, so we're going to give the students a good, decent amount of time to try to figure this out, and got to help them through as they go. And so let's pause the video. Okay, let's unpause the video. So how do you think we might want to approach this? Well, one way we can do it is we can go and try to simplify this block diagram. In particular, what we can see here is if we call this thing, all right, we're going to call this thing E of s just like we had. Now, we're going to go and call this internal signal something. Let's just give it a name. So I'm going to give it a name N of s. All right? And what we can see here is what we can do in order to simplify this thing is just try to go and figure out, well, what is the mapping that goes that deals with this whole system? Namely, as N of s goes in, we get a y of s coming out. Because remember, this y of s, all of these signals are just, you can think about it just wires splitting out, all carrying the same signal, y of s. So what we're going to try to do is do this intermediate step. So again, if this was a real challenge, we might want to stop the video again and try to figure out, well, what is the system that takes N of s and gives us y of s? So if we need to, we'll stop the video. Otherwise, we're just going to keep going. All right. So we'll do a little bit of algebra over here. And what we're going to have, let's give this thing a name. Let's call this M of s. All right. And we can do very much like what we did the last time. We're going to have M of s is equal to delta of s, y of s, okay? And then we're going to also have sorry. I messed that up. So what we're going to want to have, so M of s is equal to, delta s is actually equal to N of s minus, so that we get the N of s coming into here, and then this intermediate signal is this minus what's out of here, which is delta s minus y of s. All right, so we've got that expression for that intermediate signal. And then we know that y of s is equal to p of s, m of s. So just like we did before, we can now go and we can eliminate that internal signal. So we can eliminate that internal signal by taking this thing and plugging it into here. We get p of s is equal to n of s. Let's erase it like that. Minus delta of s, y of s. And then we can take this to the other side, giving us 1 plus delta of s, p of s, y of s is equal to ps ns. I think I messed up my last calculation. I think I only found the thing for E. We're going to have to go back and fix that. But before we fix that, we'll fix that once we do this. Sorry about messing that up. Sometimes algebra is hard. So we get y of s is equal to p of s over 1 plus delta s, p of s, n of s. Okay, cool. So let's take a moment. You may want to stop, pause the video just so everybody can calculate this down. But we've got this, so we're going to take this intermediate step over here. All right. So maybe pause the video. All right, so remember, we want y of s is equal to g of s, x of s. So as we go, we're going to find out, we're going to fix the mistake we made before. Because, yeah, we did make a little bit of a mistake. So what I'm going to do is I'm going to copy this. I'm going to put this thing over here. I'm going to call this thing p tilde. Yes. This whole fraction that we have over here. So I can go and rewrite this thing as x of s e of s, c of s. So I'm going to rewrite this whole block of terribleness as p tilde of s y of s. And if I let L of s is equal to cs ps, cs p tilde of s, then this thing is the same exact thing as x of s, e of s, L of s, y of s. Right. So I'm gonna go pause this video here, and then yeah, hold on. All right. So we are gonna go fix the egregious algebra error I made in the last one. I would have tried to do this with video editing, but I don't really have that much time, and I don't know how to edit videos. So otherwise I would have fixed it and been like, yeah, who's so awesome? Who did it right the first time? But that's okay. So we're gonna fix it now. So what we saw here was we could go and find an equivalent system for this. We call it p tilde, and then we could collapse these two systems together and call it L. And now we're left with that classical feedback loop that we had. So what I'm going to do is I'm going to finish up figuring out what this g of s is by just, first I'm going to write down what all of our intermediate bits are. So I'm going to erase this intermediate thing over here. So I'm going to keep this up because this is what we want, right? And then I'll show our intermediate calculations here. So in particular, our L of s is equal to cs times ps over 1 plus delta s p of s, right? That's our L of s. And we have this equivalent block diagram. Once we've defined this thing, we've got that equivalent block diagram. And we can go through figuring out exactly what that transform is, what that transfer function is from x of s to y of s. And so let's just go do this. All right. So we have that e of s is equal to x of s minus y of s. Y of s is equal to L of s, E of s. Or plugging this in, it's equal to L of s times x of s, y of s. And my unforgivable mistake last time was I accidentally dropped that L. It's unforgivable, at least for me, as someone who does control systems. And I apologize for my failure. Okay, so what we have is this. L of s, x of s. That was my mistake previously. I forgot the L of s. And so we see that our y of s is equal to L of s times 1 plus L of s, x of s. All right. So our final thing, our p of s, our g of s, is actually equal to L of s over 1 plus L of s, where this is our L of s. Now, if we really wanted to, we could go and chuck that in. Well, let's just go do it. It's a simple exercise. It's not like a, extraordinarily, interesting one, but it's, we can see it, just to give you an indication of how sort of easy these things are to work with and the kinds of things that you can do with them. So let's just chuck this thing into here. So let me erase all of these intermediate calculations. You may need to pause it in case anybody needs to copy stuff down. CS, PS, 1 plus delta S, PS, 1 plus CS, PS, 1 plus delta S, PS. So oftentimes when we're doing this, we like to get things in sort of simpler forms so they look like rational functions. So one of the things that we can do here is we could take this denominator and we can go and just move this denominator from here down to here, and we can see that that actually cancels out with what we've got over here. So in particular, if I take that denominator down, I get CS PS 1 plus delta S PS plus CS PS. All right, so that actually, despite all that, it looked like it was going to be pretty nasty. That's actually not that bad. Cool. All right, so in the next bit of this, we're going to be talking about, how to use feedback to give stability. So the last thing we're going to talk about in this lecture, and I guess in the class, is how we can use feedback to stabilize systems via applying just a simple controller. And in this case, we're just going to use static gains. And so if you want to do more of this stuff, you have to take a control systems class. So the simplest one of the simplest things we can look at is we'll take this thing here. We're going to make our little feedback system. This K, this is going to be a constant gain. We'll call it a gain. And then we're going to apply it to an unstable plant. So simplest unstable plant that I can think of looks like this. So we got our y of s over here, and then we're going to get a negative feedback over here. So our x of s. All right? And so in this case, this is a special case of this is what's called a plant. And it's unstable. Why is it unstable? We talked about this, I guess it would have been last week, but it's this week when I'm recording it. It's unstable because it's got a pole in the right half plane. That's right. Where is the pole? It's at 1. So it's got a pole at 1, and so anytime you have a positive pole, the thing is going to be unstable, or a pole with positive real part, the thing is going to be unstable. Because as we saw, stability corresponds to having the imaginary axis contained in the region of convergence of the Laplace transform. So this thing is unstable. So what we're going to want to do is make it so that the overall feedback system is stable. Now this corresponds to that feedback loop that we saw from last time with L of s is equal to k over s minus 1. So just now. So that tells us that the overall transfer function, T of s, based on what we saw before, is, okay, actually before I move forward, I want you to find a gain k, a constant gain k, that makes this thing stable. So, meaning that makes the overall system T of S. So, we have y of s is equal to T of s, x of s. I want this system to be stable. So let's pause the video and figure that out. All right, bring it back. The T of s, based on what we had seen before on the correct derivation, L of s is equal to that, which is equal to k over s minus 1 over 1 plus k over s minus 1. So how are we going to simplify this thing out? All right, so what we're going to do is we're just going to take this denominator, bring it on down, and we're going to have k of s minus 1 plus k. All right, so how can we make this stable? Anytime that we just need to make the poles in the left half plane. So this is stable for any k greater than 1. Or any k greater than 1. All right, cool. Awesome. So let's go and repeat this similar analysis with a slightly different system. And let's just do it in discrete time. All right? And we'll see that the techniques work out really, really similar. So discrete time, we're going to put a little z there. And let's make a different unstable system here. 1 minus 3 z inverse. YZ, and all of a sudden now we have a discrete time system. And so let's stop. Well, so what we're going to want to do here is we're going to want to go and find a k that makes this thing stable. And so what's the condition for stability in discrete time? All the poles have to be strictly within the unit circle. That's right. All the poles have to be strictly within the unit circle. So we're going to have to find a gain k so that whenever we take the feedback and we find the transfer function from x of z to y of z, that system is stable, has all the poles within the unit circle. So let's do that. Stop the video. All right, start the video. Now you're going to have, remember, y of z is equal to L of z over 1 plus L of z x of z. So this is the transfer function where L of z is equal to k over 1 minus 3z inverse. 3z inverse. So we can go and simplify that thing down, and similar stuff is going to happen. Okay, 1 minus 3z over 1 plus k over 1 minus 3z. And then we can go and pull this denominator down, and we get a k over 1 minus 3z plus k. But we've got to be a little bit more clever here than we did in the continuous time case, but not that much more clever. What I'm going to do is I'm going to pull out a 1 plus k, so pull out a constant, and then, so this thing is just some sort of a constant out here, and then what I'm going to have here is I'm going to have 1 minus, what am I going to have over here? So this is 1 plus k, and so I'm going to have a 3 over 1 plus k. Z. I forgot the z inverse there. Forgot the z inverse is everywhere. Forgot z inverse is everywhere. Sorry, some of you were probably yelling at the TV screen, and you should have been. Yes. So z inverse over here. So what is the condition I need for stability over here? You need the magnitude of this thing to be less than 1. That's right. I need the magnitude of this thing to be less than 1. So in other words, I need 3 over 1 plus k less than 1, which is true if and only if 3 is less than the magnitude of 1 plus k. Right. So, namely, if we took, k greater than, if we were taking real values for k, which we typically would, we would have either k greater than 2 or k less than -4. And that'll give us stability. So that's it. Any questions? I'm sorry, I can't answer them. But you could like post stuff on the forum or so on and so forth, and I will answer them. And like I said, we'll try to schedule a review session, and I will list the practice problems that will be useful for studying. Okay, it's been a fun year. Okay, bye.